This video is aimed at a general chemistry class looking at transition metal compounds. So the first topic here, we're going to start to look at crystal field theory. And crystal field theory is a large topic, and this first slide is just looking at d-orbital splitting. So here d-orbitals represent the orbitals in the periodic table. We know that there are 5 d-orbitals, and I've given it a good attempt to draw them here. We have the dz squared orbital, which essentially I've drawn here as black lobes on the positive and negative z-axis. That's what the two z's mean. And then we have a torus or a donut that goes along the xy axis. We have the dx squared minus y squared. The x squared just means plus or minus x, the y squared means plus or minus y, so these lobes point along the plus or minus x and y axes. And the minus sign just means that the x and y axis are orthogonal, or they're in different axes, so you can move along one axis and not move along the other, so you can move along the x-axis and not the y. Then down here we have the dzx, where the lobes are between the z and the x-axes, so I've tried to make it look like it's between the z and the x-axes. The dyz, or the dzy, whichever you prefer, where the orbitals are between the y and the z-axes. And then finally the dxy orbital, where the lobes are between the x and the y axes. So these green spheres represent 6 ligands that would, imagine these 6 ligands are full of electrical charge. There's going to be an interaction between the electric field brought about these green electric charges and the electrons which are allowed to reside within the d orbital. So these 6 peripheral ligands on the positive and minus aspect of each 3 axes, so plus or minus x, plus or minus y, plus or minus z, they're going to impose, they're going to interfere with the electric field of the d orbitals, and they are therefore going to split them. So that's what we're going to look at. That's what d-orbital splitting is all about. One thing that I do want to point out at this point is you notice that these first 2, if I can get my pen to register, these first 2, the dz squared and the dx squared minus y squared, we're going to refer to those as the EG orbitals, or they're in an EG energy level. The name EG, it's an E with a subscript G. It's not really relevant to us at this point. It's just a label for now. So we'll have a look at that. And then the final 3, the dzx, the dyz, and the dxy, we're going to call those the T2G. Lowercase t and then a subscript 2g. Again, we can go into what these labels mean, but it'll just take up time. At least at the general chemistry level, we don't need to do anything more than just name them. But the thing we should point out, there's, instead of 5 degenerate orbitals, the splitting caused by the proximity of the ligands, these green spheres I have here, we've now got 2 separate collections of orbitals. We've got a collection of 3 and a collection of 2. We've got the collection of 2, the EG set, and then the collection of 3, the T2G set. We know that these are different. We know that the EG set is going to have higher energy because there's greater electric repulsion, because we can see that the green ligands are pointing directly along the axes, and they're headed directly towards the orbital lobe of the metal. So that's a direct head-on collision. And then the T2G set, it's slightly off. It's a diagonal interaction, right? So we can see it clearly here. The ligand is approaching along the axis, but the orbital of the metal is pointing between the axis. So there's not a head-to-head interaction of orbital density. So the repulsion of electric fields is lower. So the T2G have a lower energy because of that, and the EG have a higher energy for the same counter-argument reason. Okay, so moving on to our next slide. So let's insert a slide. Okay, let's move on to the next one. So let's draw this. I'm going to call this an octahedral field because that's what it is. So this is when essentially we have what you've just seen in the previous slide. We have an island. Three levels we've called T2G. Two levels we called EG. We've got energy going that way. And originally, we had our 5 d-orbitals. So this is the 5 d-orbitals. So here there's no field splitting. It looks like they all have a slight variation in energy, but that's just the way the diagram looks. But these have a fixed energy level, and then we can split these degenerate orbitals into the EG set and the T2G set with the presence of an octahedral field, octahedral field splitting, and I'm going to call that delta O. Delta just means change, O means octahedral. We'll call this energy level here the barycenter. This is the original barycenter. So the EG level is higher energy than the barycenter, and the T2G level is lower energy than the barycenter. Let's change the color of our pen. So this whole thing here, I can draw it straight. This whole thing here we'll call delta O. That's the total field splitting. But then we'll notice that we have above the barycenter and we have below the barycenter. Above the barycenter we have 3/5 delta O. Below the barycenter we have 2/5 delta O. Clearly, if we sum both of them, 3/5 plus 2/5, we have 5/5 or just 1 delta O. The 3/5, some people like the fraction, some people like the decimal. So we can 3/5 is 0.6. So it's 0.6 delta O. And the 2/5 is 0.4 delta O. So you'll sometimes see the decimal, you'll sometimes see the fraction. Okay, what else do we know? We know that delta O, so let's go back to black here. So this octahedral field splitting here, this delta O, we know it's a quantum energy value. So let's call this an energy value E. We know therefore this is equal to hc over lambda. And possibly not in this video, but in another video, we'll convert that to a value called wave number. So we'll say that that's equal to hc nu with a squiggle on the top, where this is wave number. But more about that in a later video. Okay, so we have splitting in an octahedral field. So definitely we've seen what the orbitals look like. Now we've summarized it in a diagram that will be very useful to us. Now, I want to next talk, so I'll insert a new slide. I want to talk about weak and strong field ligands and how we can split the field to varying degrees. So let's insert a new slide. Okay, so let's insert a new slide so we can have, we'll call this weak field versus strong field splitting. Weak field versus strong field splitting. So there's our original d-orbitals. So let's say that we have, let's put some electrons in. Let's put 4 electrons in here. So there's 1, 2, 3, 4. So I put 4 electrons in that weak, d-orbital here. So let's say we have a d4 system. This is a free atom. So there's no field splitting here. No field to split into the Eg and the T2G. And now we'll have the weak field on the left. Okay, so there's the barycenter. So this will be the weak field. Weak field splitting. And then we'll have the strong field on the right. Strong field here is just greater splitting. So this would be the T2G of the weak field and the Eg of the weak field. This would be the Eg of the strong field, the T2G of the strong field. Strong field. Okay, and we've got the barycenter still. Okay, So let's see what happens to our 4 electrons in these different types of fields. Okay, well, we know that the electrons in this case would fall into the T2G level. So we would have Hund's rule, fill each orbital once before you pair them up. Now because it's weak, it's relatively small, so we would then therefore continue to fill each orbital once before we double up. So if we had a weak field, if we wrote the electron configuration here, it would be T2G3 EG1. So there's our 4 electrons. So we've got 3 electrons in the T2G level and then 1 electron in the EG level for our D4 metal. In a strong field, it's much larger. Delta O is much larger. So we would actually pair up first. Let's get our red pen again. So we'd have Hund's rule, Hund's rule, Hund's rule. That's too far to be promoted, so it's much easier energetically to pair. Pauli exclusion principle. So we would get a completely different electron configuration. So in this case, D4 would give us T2G4. So notice there's a difference based on the electron configuration in the weak field and the strong field. So why is this the case? Well, in both cases, this is delta O. But in the weak field case, delta O, that energy separation is less than P, where P is the pairing energy. So let P equal the pairing energy. So remember, electrons are like charge. They don't like to be close to each other, and it costs energy to pair them up. Well, to avoid pairing them up, if you can jump, because the jump energy delta O is less than the pairing energy P, then you will jump. Okay, and the delta O in the strong field case, here delta O is greater than the pairing energy. So if the lowest energy thing happens first, you're going to pair before you jump. So you just pair up. Okay. This has consequences for the spin. So let's change the pen color to green. We won't talk about spin too much in this video, I don't think, but we'll just mention it in passing. The strong field ligand is produces a low spin complex, and the weak field ligand generates a high spin complex. So let's see the origin of this low and high spin. So let's say spin S is the sum of all of the spins of each individual electron. So if we look at the spin for the weak field case, then we've got we've got 3 electrons all pointing up, and then a 4th electron pointing up. So it's going to be 4 lots of a half, which is 2. And then for the strong field low spin case, we have S is, well, now we have 3 up and 1 down, so the down spin cancels one of the up spins. We have 2 net up spins, so that's 2 lots of a half, where each electron is spin a half, and that's just equal to 1. So we can see that the high spin is because 2 is higher than the low spin of 1. So we can quantify the spin of 2, we can quantify the spin of 1, because 2 is higher than 1, 2 is the high spin complex, 1 is the low spin complex. Okay, so that's hopefully straightforward. Let's insert a new slide. Okay, so we've got the spin. What did I want to talk about now? Yeah, okay, so we've got the spin. I think now I want to go right to linking. So the little bit of a background there on the field splitting, like here, that was to get us ready for something that's going to come up in a few minutes in this video called the chelate effect. So that's a little bit of background. Okay, I would like to now talk about stability constants. So essentially, just to orient this a little bit, we started off by talking about crystal field splitting when ligands approach a metal atom, and then we had a little look at what that might look like from an energy point of view, about separating the energy levels of orbitals. Now I want to look from a thermodynamic point of view at the equilibrium constants associated with this splitting. So I'm going to call this stepwise stability constants. And I'm not going to do it in red. I'm going to do it in black. Thank you very much. Stepwise stability constants. Okay, so if we have a metal and it adds one ligand, that could give us, let's say it's an equilibrium, that could give us the metal and the ligand as a complex. Well, that would have an equilibrium constant, let's say the first equilibrium constant of a dilute solution, so we'll use concentration. The concentration of the product over the product of the concentration of each ingredient. We could then go on and have the original product add a second ligand, and that would give us the metal with 2 ligands with different species. Therefore, it would need a different equilibrium constant, and that could be represented as Ml2 over Ml and L. I'll just do a couple more. We could have Ml2 plus another ligand to give metal ligand 3 complex, and then the equilibrium constant for that would be Ml3 over Ml2 ligand, okay, etc. for more than 3 ligands. So we could call these each K, we could call a stepwise stability constant or an equilibrium constant, which is essentially what it is. And it's stepwise because we're taking this in steps, right? So we've got step 1. We're looking at everything happen one step at a time, etc. And these obviously are the constants, right? Okay, so we've got these stepwise stability constants. Typically, K1 is greater than K2 is greater than K3 is greater than Kn. Typically. Now this is typically the case, and we're going to argue this case based on entropy. So it's an entropy driven process. So let's try and link it with entropy real quick. If we look at the first step, or prior to the first step, the reason why, if we were to add, let's say we added let's say we had 10 molecules of M. Then initially, for step 1, 100% of our M would be ready to undergo step 1, right? To actually form the Ml compound. 100% of the metal would be available. But then to produce Ml2, we only have a fraction or less than 100%, because some of it will be M and some of it will be Ml. And it's only the fraction Ml that's available to become Ml2. Likewise, even less still, a fraction of that fraction would be available to produce Ml3. So let me see if I can see here. We have 100% M can produce Ml, but then we have less than 100% Ml can produce Ml2, and then we have less than 100% of Ml2 can go on to produce Ml3. But the fraction that's Ml2 itself is less than 100%. So we have this cascade process where we have a reduced supply. So we have a diminished and increasingly diminished K value. Okay, so keep that in mind, these stepwise stability constants. We can have an overall stability, so rather than like stepwise, we can have an overall stability constant. Let's have a look at that. So we can have overall stability constant. Okay, so if let's see, I'm going to try my best to copy this. Let's see if I can copy it down here. Yowza, that looks busy. Okay, so I've copied it. Let's get rid of the step 1 stuff, or the red stuff I have here. So I can clear that up a bit. Okay. Oh, yeah, I can get rid of that. That's a quick way to... Oh, I want to get rid of that. Alright, let's see if I can get rid of that stuff at the bottom. Okay, that'll do. So let's say this is our final product, this K3. Okay, so if K3 is our final product, then we can write the overall stability constant beta. So we can write that as beta 3 is ML3 over ML cubed. Okay, cubed because there's 3 L's. So here it's not looking piecemeal, so compare beta 3 with K3. K3 and beta 3 have the same numerator, but K3 is looking at just this final step, so the single process of producing ML3, whereas beta 3 is looking at essentially the product of K1, K2, and K3. So we've got a relationship between the overall stability constant and the stepwise stability constant, overall as a product of all the stepwise. So in general, beta to the n is going to be MLN over ML to the nth power. Okay, so we have a way to use our thermodynamics to look at, to start to look at these complex materials that we're looking at in this chapter, these coordination compounds eventually that we'll be introduced to. Okay, let's look at an example. Let's look at a specific example. Okay, so we're going to look at Bronsted-Lowry acidity of the hexaquo-ion. Bronsted-Lowry acidity of the hexaquo-ion. Okay, so essentially we're looking at a metal. Hexaquo just means 6 water, so we have 6 water ligands. That's our octahedral field. So the electrical field of these 6 water ligands is influencing the metal. This will have a variety of charges depending on what the metal is. Now, if this is in solution, we can have this in the presence of water. So we could have, let's see, this could be aqueous, this could be water liquid, This will be in equilibrium with metal, 5 water, OH, and now we've got N-1 positive charges. That's aqueous, and now we've generated a hydronium ion. Okay, so if we've generated a hydronium ion, we could say that this coordination compound here is an areneous acid. Different definitions of an acid it will satisfy, but areneous is a quick one. We notice we produce hydronium. An actual example of this genetic template would be an ion complex. So let's have a look. Iron, 6 water, ligands. This would be iron 3. We could add that to water. It will be in equilibrium with iron with only 5 water, a hydroxide ligand. This would therefore be 2+, aqueous, and we've got hydronium. And if we were to look at the K1 value of this, so we know that K1, this would just be iron, H2O5, OH, 2+. We'd have to put the whole of that in square brackets. Then we'd have hydronium. And we'd have to divide that by the original compound. And then put the whole of that in square brackets. We ignore water because it's a liquid. Well, let's say that K1, well, it would have a value. If we then went on to look at K2, then we could have iron, so the product from our original expression we could add that to water. It would be in equilibrium to give iron with only 4 water. As soon as I said 4, my brain wrote 4. How limbic of me. Aqueous plus hydronium. We could have K2. K2 would therefore just be iron, H2O, 4, OH2 plus, whole thing in square brackets, hydronium, and then the denominator would be the original reactant. And we know that K1 would be greater than K2. Okay, and this could go on to K3, etc. Okay, so we can start to write equilibrium constants for this type of material. What can we do with that? What might some insights be of doing that? Well, let's have a look. Well, first of all, we notice that we definitely can use Le Chatelier's principle here. So in both of these K expressions, we have an acid as a product. So we could definitely since hydronium is produced, we could definitely favor the forward reaction with higher pH. So that would be Le Chatelier phenomenon. So we could definitely do that. What would happen at K3? I think it's worth looking at K3. We didn't have space to put K3 on the last one, but if we look at where we got to with K2, then we would just have Fe H2O 4 OH2 aqueous plus water liquid. Then we would form Fe H2O3 OH3 no charge, so this would now be a solid, and so this would precipitate out because it has no charge. So this would precipitate out because it has no charge. Again, these are all entropy-driven processes. These are all entropy-driven processes. We can see clearly that you've got 6 water to interact with, so greater favoring of the forward reaction here. But as you go on and on and on, as the number of Ks increases, here you've only got 4 left, so you've got 2 fewer options, so that would be a statistical availability issue, which therefore would label it as an entropy-driven process. Okay, I wanted to build upon this by looking at the chelate effect. So what on earth is a chelate? Because chelate effects can influence this hierarchy of K values. So I'm going to call this the chelate effect. On ordering of K values. Okay. Okay, so let's see what would be the best way to introduce this. Essentially, a chelate ligand is a type of ligand that can occupy more than one spot around the metal. You can have bidentate ligands, which occupy 2 spaces. You can have tridentate that occupy 3 spaces. So let's consider something called, it's commonly called the Bippy ligand. Where Bippy is just short for bipyridine, so it's got 2 pyridine rings. So this is just going to be 2 pyridine rings joined together. With its lone pair here. So let's have a look. We could have iron, hexaquo-ion. Let's consider iron 2+ here. If we add Bippy to that, we can have equilibrium constant K1 to give iron. There's only 4 now because the Bippy occupied 2 spots. So we've got 1 Bippy, but 1 Bippy occupies 2 spots. We've lost 2 water. We've now got 1 Bippy, but neither one has altered the charge. So we've kicked out 2 water molecules. And we know that K1 is going to be, let's see, in this case it would be metal with the new ligand Bippy. Or here M stands for this whole metal complex. L is the ligand Bippy over the original complex and Bippy itself. So here we'll call this, this is M and this is L. Okay. If we go on to look at K2, then we'd have the product from the first reaction. So we'd have Fe H2O4 and then we'd have Bippy You could put aqueous here. I'm not going to bother because hopefully it can be assumed now that water is a liquid and everything else is aqueous. Let's add another Bippy. Another equilibrium expression, but with a different constant K2. This would be iron H2O2. We've lost another 2 water. And now we've got an extra Bippy. So Bippy 2. Still got our 2+ charges. We've lost another 2 water molecules. And now K2 would be the original compound, but now with 2 Bippy. Over the original compound, which had 1 Bippy and an extra Bippy. And then finally, because we only have 2 more waters left to lose, so this will be our last round of Bippy. Fe with 2 water molecules. and 2 bippy. Let's add our third and final bippy. Establish a new equilibrium constant K3. We have iron now with 3 bippy. 2 plus, and our final 2 water are lost. And now we'd have K3, which is our new product with 3 bippy over our original product and the extra bippy. Okay, so here what we notice, the chelate effect, is we actually see, as expected, K1 is greater than K2, but then the whole thing is a lot less than K3. So this sudden change around is the chelate effect, and that's instead of what you might expect, which would be K1 is greater than K2 is greater than K3. So here there's no chelate effect, but here we have a chelate effect. So let's see if we can understand what's going on. So let's see if we can understand what's going on with this chelate effect. Okay. So I'm going to call this understanding why K1 was greater than K2, but they were both a lot less than K3. So understanding this chelate effect. Okay. So bippy is a strong field ligand, and because it's strong field ligand, it implies it produces low spin complexes. It also implies that delta O is greater than the pairing energy. So remember we looked at the difference between weak field and strong field ligands and pairing energies and whatnot a few slides ago. So the products that we had up until the K3 part, so iron H2O6 2 plus, that was our first product, well that was our reactant. Our first product was iron 4 and a bippy. Then we had iron with that one. Well, these are all high spin complexes. So these are all high spin complexes, and recall that this was where K1 sat and this is where K2 sat. However, the final product, where K3 was involved, is a low spin complex. This is a low spin complex. Now, if you recall what that means we haven't actually done any crystal field stabilization calculations, but the low spin complex on the right here, we have this increased stability. So rather than being elevated above the barycenter, we've got more electron density, more likely to have more electron density below the barycenter and further below the barycenter. So we get this stability effect. Okay, so keep that in mind. So this increased stability, that's what's responsible for this large K value. Its increased stability is responsible for larger than expected K3 value. So to use the language of equilibrium, it's shifted right much more than expected because the product is thermodynamically more stable. So that would be a feature that I'd want to point out to my class. Okay. This video is creeping up to about an hour, so I'll cut it short there. There's a couple of bits and pieces I wanted to do. They will just start us off in the next video.